Oj, nu spelar de in här. Mm. Bra, då så. Då är det dags att köra igång dagens föreläsning om multimedia och telefoni på internet. Ska vi byta till mixläget här. Och det fortsätter lite grann på det som vi pratade om förra föreläsningen om quality of service. Så vi kommer länka in lite grann till det. Därför att det är ju någonting som behövs kanske när man kör en del av de här tillämpningarna. Lite definitioner först. Multimedia, det är ju att vi kombinerar olika typer av media. Och rent generellt så kan det ju vara som här fotomusik till exempel, audio och video, det kan vara text. Och när multimedia kom en gång i tiden så såg man en länk som en del av media, så hypertext, också en form av multimedia då. Så att det finns ju massa olika typer av medier man kan kombinera på olika sätt givetvis. Vissa medier är ju enkla att kombinera, vissa är mer svåra. Sen har vi då realtid. Jag inser att nu kör jag på svenska, det ska jag inte göra. Sorry, I'm switching to English now for stream. Sorry, I just have Swedish students here in class. Right. So, multimedia combining several types of media. And then real time refers to media then that needs to be presented in a certain sequence or a certain aspect of time. And typically we talk about audio and video, of course. If we have an audio stream, then it's of course important that that audio stream is timed, so we don't suddenly have delays. Sorry, someone on Slack says that the stream is not on, but I see it is on. Let's see some reply as well. Yeah, great. So the time of multimedia we'll look at today is real-time multimedia, of course. And then we talk about sources of the information. And since we have a network, the source is somewhere else on the network, and we have a playback somewhere. So we fetch from the source, and we can fetch from one or we can fetch from several sources and combine that information. And if we combine, then of course it's even more important that we can time the information and link them to each other. Some more definitions. Playback is then when we actually show the information. So we have it from a server somewhere, we create a stream, and then we accept that stream on the client, and then we make the playback. That is when we show that information. Sample rate is how often we sample a signal. So, I mean, when we are sending on internet, we need to digitize the information. And when we digitize the information, we first have to choose a sample rate, regardless of what type of media we're talking about. So that is how often we sample the signal. And then we also need to decide on the resolution. How much information do we actually capture each time we sample? So, for instance, sample rate could be 8,000 times per second, 8 kilohertz. And that is what is used for instance, pulse code modulation that is used for internet telephony, and that is sort of a standard for sound. We quite low quality, of course, but still enough to work as for an audio stream. And then we have synchronization. And synchronization is then if we have multiple sources, we need to synchronize them. So if we have one video source and one audio source, and they need to be synchronized in order to actually give a meaningful playback then. So now we have servers who present a stream of different type of multimedia. And of course, each stream had to be coded somehow. We have to decide, okay, how often should we sample, at what resolution, should we perhaps do some type of encoding of it, mark it up with some type of metadata, or whatever. There are lots of things that we need to decide on. And typically each source chooses how to do that, and then the client have to live up to that and adapt to it. Sometimes we can have a discussion, so we can have a negotiation between client and server what we should have, but eventually the server will choose something, of course. So for instance, a video stream might then be 30 frames per second and use some encoding of the picture that uses compression, which means that when we accept it, we need to decompress each frame. We might even, as we'll talk about later, use a compression scheme that uses different type of frames. Sometimes, now and then, we send a complete frame, and then for a while we only send updates of that frame, which is much smaller than the entire frame. And then we send the entire frame again, and then updates. That's one way to compress the information. And then at the same time, we might have an audio stream then with 8,000 samples per second then. And now they need to be synchronized because they are, of course, not, they don't have the same sample, and they still need to be synchronized in order to be relevant when we play them back. So we need to be able to handle different encodings, and we need to be able to synchronize them, even if they are done differently then. So we start with the source. The source has some type of stream or some type of data source that need to be digitized. We do that by sampling them. And then we generate the data. Typically we sample for a while, and then we put that information into a datagram. And then, as you see later on, we have to decide for how long should we sample before we actually send something. But we do generate a number of data packets, and then we send them onto the channel. And now is the question, what is that channel? And if we have an ideal channel, ideal as we talked about last time, an asynchronous network, we can send a data packet at any time when we have it, and it will be delivered through the network at the same rate and delivered to the destination in the same rate as we presented to the network. So that would be an ideal situation. And if we do that, our problem is quite simple then, because we don't have to really think about much about synchronization. We just create the stream, and then we play up the stream as it's come, and everything will work. Unfortunately, we rarely have these networks with this ideal transmission channel. But that would be, if we go back to the last lecture then, a quality service where we have a constant bit rate. That is the negotiation between the network and the receiver. Latency is something where we couldn't get away with, of course. There will always be some latency. But as long as the latency is the same, which is that we don't have any jitter, when we do the playback, we don't notice that, because we start the stream, and then maybe, as in this example, 200 milliseconds later, the client can start to play back that stream. And if it's 200 milliseconds or 100 milliseconds, doesn't really matter. Of course, if we have a situation when we need to send something back, then it's a different thing. Now the question is, even if we have this ideal channel, we still have to think about how to packet our information. Because normally we do have packet delivery in a network. If you talk about the internet, we do create datagrams, and that is what we deliver in a network. There are, of course, networks where we encode on bit level and send just one bit at a time. If we just have a transmission line like a fiber optic cable directly between sender and receiver, we don't have to pack it, we can send the bits directly. But in a normal network we have to packet it. So then it's the question, okay, a sample, how big is a sample? Well, that depends, of course, what the source is and what type of encoding we are doing. If it's video and we have an 8K resolution, something like that, and we make a sample, that is quite big then. But if we take an audio and the PCM and the coding, each sample is just 64, let's see, 8,000, yeah, each sample is only 8 bits actually. So now that we want to put that on the network, well, we can of course take one sample and put it in a datagram and send it. And on the other side, when we get them, we play them back. And as long as that is all the traffic we have in network and we don't have any jitter, that would be perfect all right. But if we have other type of traffic in the network as well, we will see that this type of transmission will be adding a lot of overhead, because for each packet, these 8 bits, we have to include an entire datagram header with, what is it, Fiber version 4, we have at least, what is it, 50, 60 bits at least, something like that. So it will be a lot of waste of bandwidth here to do that. So instead we probably want to combine a number of samples in one packet before we send it. And that means that we don't have this nice situation anymore, and we can just take a packet and play it back, because now we sample for a while, maybe 100 milliseconds, combine a number of samples in one packet, send it, and if we play them back directly, we would play back 100 milliseconds maybe just in 1 millisecond, and it wouldn't sound very nice, of course. And then we would have 99 milliseconds without any playback at all. But that means while we are gathering these samples, we have a delay. We don't do anything on the network. And then we send a packet. And then there's a long delay again, and then we send packet. So we introduce delays for each sample then. So here we have an example of that with PCM then. 8-bit, as I said, we sample each 125 microsecond. If we just look at it on a physical network, we have an Ethernet here. An Ethernet has 1500 octets payload. And then a header that is not that big, but still, anyone who knows an Ethernet header, how big is that one? We have CRC checksum, we have a type, byte, we have an address, what is it, 20, 30 bytes, something like that perhaps. But right, the payload is 1500 maximum. If we then wait until we have filled the entire payload, as you see, it will take almost 200 milliseconds to do that. And during that time, the client doesn't see anything, and then we'll get 125 packets at one time. So more packets with smaller content means that we had more overhead, but on the other hand we have less delay. So the question is, what is the best here? Now, on internet and on most networks, we don't have this ideal transmission channel. So instead what we have are problems that we must handle. We must handle lost packets. Packets can be lost for different reasons. It could be a noise that just erases a packet on the transmission line. It could be that a buffer is full, so they have to drop it. We can have duplicate packets. That can happen if we think that the packet has been lost and we resend it, but actually it wasn't lost. It was just our misconception. So now we have two packets of the same sort. Of course, we will have variance in delay. We will have jitter on a normal network, which means that when packets arrive, we couldn't just play them back because they will not be in the correct order. Or they could be in correct order, but the time between them is not correct. And if the variance is very high, or if we handle resending packet, we will also have out of order delivery. And if we just play them back when in the order they arrive, of course everything will be just garbage. So we need to handle these problems. And if you think about how to handle those problems normally, well, normally if we have something that is important, we use a transport protocol that handles those problems for us. And what transport protocol would that be? Yeah, TCP. TCP handles all of these things for us. If there is a lost packet, it will be resent. If there is a duplicate, we will see it and remove one and so on. So it handles most of these problems. Unfortunately, that is not a good idea for streaming media. Why not?
Because it will take time to resend.
It will take time, exactly. If we have one lost packet, TCP will stop and say, okay, you have to retransmit that one, and then when we get it, now we can continue to receive packets. But in a stream, we don't want suddenly the stream to stop for half a second and then continue. It's better to just drop a packet. Say this PCB encoding and for sound. If we make 8,000 samples per second and we lose one of those, we won't notice the difference. The playback will still be almost the same. Even if we lose 10 of those 8,000, we will still hear almost the same thing. So it's better to just drop those packets that are lost. Don't bother with retransmission. So that's something that we have to think about. Another thing is that jitter is unavoidable. We will have jitter, and that of course will influence the possibility to have a smooth playback. So we need to handle it somehow. And what we do then are two things. The first is that we add timestamps. So the idea is that any time that we sample something, we put a timestamp on it. And when it arrives to the destination, we know where that packet or that sample belongs in the stream. So the sender adds the timestamp, and it's relative to a start of a stream. And we don't bother with having absolute timestamps, because as I talked before, we have problem with synchronizing clocks, so we couldn't use a normal clock. We use relatives to the start instead. So now we know that, okay, this small sample here should be 1 minute, 2 seconds, and 5 milliseconds into the stream. That is when this should be played back. That means that whenever a packet arrives now, we can see in the timestamp when it should be played back. And that means we can rearrange all the packet when we arrive and make sure that we play them back in correct order. And if there is a packet that is late, it may be so late that we already passed that time in the playback, and then we just discard it, of course. We don't have use of it anymore. The second technology we use here in order to handle these problems on the internet is a Jitter Buffer. And that is handled by the receiver. And that works like this then, that when we start the stream, we don't start playback immediately. Instead, we are waiting for a while and buffer incoming packets. And once our jitter buffer is full, then we can start the playback. And now we play back and receive, hopefully at the same rate. If our jitter buffer is too small, we have a problem, because then packets can arrive and don't fit into the buffer, and then we have to discard them. So we don't want to do that. So we have to make sure that we can remove packets from the buffer at least in the same rate as they arrive. And of course, that means that we have to probably throttle the sender. And that's quite natural how we should do that, because the playback should be in real time. And then we know the data rate of that stream normally. So that's rarely a problem then. But on the other hand, if there is a problem in the network, so suddenly we have a delay, it takes a while and no packet arrive, well, we can still pick packets from the buffer and continue to play back at a normal rate. And then the packets arrive, and now maybe a whole chunk arrives at the same time. And then we just fill the buffer again. And so the idea is that the buffer can go in and out like this. The end of the buffer can be filled up, or we can have a delay, but there will always be at least one packet in the front here, so that we can, at a regular rate, consume packets from the jitter buffer. So this is what we see. You're probably seeing that when you stream a video or something on internet. When you start it, it takes a while before you can actually start looking at it. And that is exactly what is happening. They are filling up a jitter buffer. And sometimes that is not enough, of course, because sometimes you have so much trouble in the network that it holds for a while, and you empty the jitter buffer, and then you don't have anything to consume, and then there's a break in video signal, and then it loosens up again and they fill, so it can start again. So there is a limit for how big that jitter buffer is, of course, and if we have a very long jitter buffer, it both takes resources, but it also means that there's a long delay before we can start looking at something, and we don't want that. So there's again, we have to decide how big that buffer should be, really. Some protocols now then, because so far we just talked about it in general terms, but there are quite a lot of different standards in this area. And the first standard we'll look at is this protocol, the real-time transfer protocol. And that is quite a common protocol used for streaming of both video and voice. And see, it's called real-time transfer protocol, but it's not really a transport protocol. It will use UDP as transport protocol, so it's on top of the transport level. The real-time transport protocol does not contain a jitter buffer. It does not control playback. That is up to the client to handle. What it does provide, as you see, are these three mechanisms. First, a sequence number. So each packet that we send have a sequence number. And the idea of that is to put them in order when they arrive packets. We might have been able to use the timestamp to do that, but the timestamp can have a resolution. It can be hard to see. A sequence number is much easier to handle when a packet arrives, to see how we should put them into this jitter buffer. So that's the sequence number. The timestamp is then used when we play back. So whenever we start the playback, we look in the jitter buffer for the first packet that is there, and then when the timestamp is correct, we play it back, and then we look for the next one and play it back when the time is correct. So once we started the stream, the time starts and we just consume data packets that have a correct timestamp. And then a third thing that is provided by this RTP is a source identifier, which makes it possible to have several streams going on at the same time and then combine them during playback. And the obvious example here is that we have a video stream and a separate audio stream, and they may come from different sources, but we combine them with the playback, so they have to be timed the same. And to make sure that we know what type of data arise, we have a source identified to sort that out. So RTP allows the sender and receiver to choose sample rate, and encoding we can negotiate, but normally it's the server who decides this is what I will send. As I said, it uses UDP as a transport protocol, so it doesn't bother with the added security that TCP gives. We want to have it fast. That's the main thing here. We have timestamps and packet sequence number. It includes this marker bit. That is what I talked about before when we make an encoding of a video stream. We have this marker bit to say, okay, this is a full frame. That means that if we for somehow lose synchronization or lose some packets, we just have to wait for the next packet that has this marker bit. And now we know that, okay, from that one we can recreate the stream again. There is a companion protocol to RTP, as you see, the RTP control protocol, RTCP, that provides some quality of service feedback. So the idea is that the client can send something back to the server and say something about the quality of service here. We can negotiate it, we can send back information about how it actually works. So that is not done by the RTP itself, but by this companion protocol instead. So that's RTP. Well, some of marking we already talked about. For video, for instance, we have these iframes and bframes. Why timestamp and packet sequence are separated is because timestamps do not, well, timestamps can be, well, the main thing is really the timestamp is used for playback, and sequence number is used to rearrange in the input in the Jitter Buffer to make sure that we know what packets have arrived and if there are some lost here. So that's RTP. This is the format for it. We won't go through all the fields, but we can talk about timestamp. You see the second row here. It's just a number, which means that we couldn't see from a packet what it means. Is the timestamp in seconds since the stream started, or is it in milliseconds, or is it some other measure? That is something that needs to be negotiated by client and server. What does timestamp mean here? But it starts with 0 then when you start the stream, and then it just goes up here. Pay type is the payload type, if it's a video stream or audio stream, what it is. Sequence number, initially chosen at random, and then it just counts up 1 for each packet. The idea why we have random start, can you come up with some idea why we should have a random start here? So no one else can guess. Well, if it were some attack, but yeah. But normally, I mean, we haven't said anything about encryption, so anyone can see what the sequence number is. So it's not really for security for that reason. But there's something else. that could be good to have a random number instead of 0.
You can have multiple streams.
Can have multiple streams with different, but that would be identified by this third filly, the synchronization source identifier. That would be different sources, so they are marked in that way. Now the idea is that if we restart, we have to start over again. By having a random, we with a higher probability can see that now we're starting somewhere else. We don't restart at 0 again, because if we have to restart over again, it would be very hard to see the difference between an old stream and a new stream, because they would have almost the same sequence numbers. But if we randomly start somewhere else, we will be in an entire other range of sequence number, and we wouldn't mix them up with old ones. So that's the main idea. And sequence source identifier, as I said here, and that can be one or additional identifiers we can combine. Question?
Is the timestamp in some way synchronized between server and...
No, it's not. So it's always just starting at 0, and that is when the server starts the stream. And then whenever they are sending a new frame that is part of that stream, it has a timestamp then relative that start. So it's up to the user, to the client then, to understand what that means and how that relates to normal time and when it should be played up. So, since RTP is not a transport protocol and we use UDP, of course it has to be encapsulated here in a UDP packet, and then a UDP is of course encapsulated into an IP packet. That can be IP version 4 or 6, doesn't matter. So we add an IP header, and then of course we have to push it onto some physical network, which means we have to add a physical frame. Could be an Ethernet frame or an SDH header, whatever. So, but that's the normal situation. It's just that we want to show here that RTP is really not a transport protocol. We need a transport protocol as well between RTP and the IP layer. The next protocol we'll look at is this real-time streaming protocol. And so this sounds like it maybe is what the previous protocol was to handle a stream. But what this protocol is really, as you see, acts as a network remote control. So the idea with this protocol is to control another stream. So with RSTP, we can ask a server to start sending an RTP stream. And then we can ask a server to stop or restart or record and so on. So it acts like a remote control for streams. So say it supports, for instance, retrieval of media. So we can start stream. We can handle conference calls, and we can record. So there are a number of what we call methods in our TSP then. So these are, you can say, commands that we can give with this protocol. So major methods set up, that is initiate, start a new stream then. Play is when we actually start showing the stream then, pause and tear down. So that's the major one to handle streams then. And then there are some additional methods that can be supported depending on the type of server and type of stream we're using. But the main part here is that we can start, we can set up a stream, and then we can control that stream and then close it down again. So these two are used together, but we need other protocols as well in order to get a full stack of protocols for a stream. So at the top here first, we need something to describe streams, because before we can actually start a stream or decide that we would like to contact a media server and start the stream, we need to know about the streams. We need to have information about them. What is available, maybe if there is a cost, some details about how it's encoded and so on. And all of that is handled by these stream description protocols that we have at the top here, like the session description protocol, SDP, or SMILE. So these are different protocols that handle the description of streams. So before we can start the stream, we need to know about it. And then we have a stream control that then can be used to start and stop and tear down. And then we have RTP, the media, which is the transport of a stream then, with timestamps and sequence numbers and so on. And then possibly below that, we might have a protocol that we talked about in the last lecture. We might want to have some quality of service on the network that will deliver this stream. So we could, depending on, of course, what is supported by that network, use some type of resource reservation protocol or diff-serve, whatever. But as we talked about last time, that is not commonly supported in networks. So it's not something that we normally will have actually. So a typical scenario here with these protocols could be like this. We are the client here, and we start with HTTP connected to a web server somewhere, surfing on Netflix, for instance, and we use the HTTP to navigate around and select different movies that we want to look at and so on. Once we have decided what we want to look at, we use the SDP protocol to get information about that stream. How is that stream set up? How it's encoded, what are the sampling rate and so on. Once we know that, we can use the RTSP protocol then to connect to that stream, get it started. And then we can control the stream using RTSP to pause and restart it and so on. And the actual delivery of a stream then is used by this RTP. So RTP is actually sending the stream with timestamps. And during that, we might use this RTCP, the companion protocol here, to send back information to the server about quality of server problems. That could cause, for instance, the server to renegotiate the sampling rate. If we see that we have so much problem in the network that we lose a lot of packets or there are a lot of delay here, we might go down in encoding so we don't produce so much data. And then hopefully we can get a more steady stream even if the quality is a little bit lower.
Is that what happens when you start, for example, a Netflix film?
Yeah, I mean, for instance, Netflix, you have an type of service that you prefer as a level of it, and they start with that. But if it fails, then it can go down in resolution. Yeah, and go up again. Yeah, if everything seems to work again, you can report that with RTPC again and say, okay, now you can try to go up again. Yep. And then when we are finished, RTSP is done again to tear down that stream. So there are quite a lot of different codes involved here, and we still haven't said anything about really how we encode the data, because that is an entire another field. I mean, what video standard are we used? How are we encoding it? How are we compressing or not? Are we at what resolution is and so on? All of that are also different standards, but that is negotiated when we set up a stream, and of course we have to conform to that. But that is not handled by this protocol. We just send the information about what we have here, what we have decided. So I think we can actually take the break already here before we move into next. So let's take 10 minutes break here. Yes.
Om man kollar på YouTube till exempel och får för sig att byta upplösning på videon. Sker det via RTCP då att du liksom
det finns ju andra protokoll också som gör de här sakerna. Så att här är inte de enda möjligheterna.
Ja, okay.
Så jag vet inte exakt vad YouTube använder som använder just detta.
Men i sånt fall
det skulle kunna vara det.
Bryta strömmen och sen lägga upp en ny då.
Nej, du behöver inte bryta strömmen i så fall. Inte om man använder ATCP, för då kan du tala om att när vi går ner och sen under pågående ström så kan du ändra upplösningen. Men om du använder andra protokoll så kanske du måste stoppa den och starta den igen. Frågorna om labb 4, ja. Ni har sett att jag har lagt ut labb 4. Har ni väl tittat på den? Någonting?
Eller jag har läst igenom lite, men alla dina videos funkar inte som stod hur man installerade. Det var någon som inte var tillgänglig.
Jaså?
Kan jag kolla på det? Det var en vecka i alla fall som inte funkade.
Okej.
Jag kan inte lösa en från med 3 förstås. Eller är det 3 eller 4?
Har vi samma? Någon sån mekanism.
Ja, okej.
Megamix, okej. Var det nu på fredag?
Jag kommer bara samla det med för det så det är ingen
Du kommer få parity.
Jaha, plockat bort den.
Men har vi samma kub eller får känna på?
Ja, den fungerar. Okej, ja, jag ska kolla den länken och då måste jag hitta en ny video. Undrar varför de plockat bort den. Det står ingenting om det, det gör inte.
Då är det en standardrörelse. Till slut så bara får du ut den.
Fick du den idag att du ska godkänna det och ta säkert?
Ja, jag hade inte mina för sista personnummer som mejlade mig på morgonen. Och bara dem då. Och sen fick jag det.
Har du varit 4? Ja, har du tittat på 4? För den gjorde inte Stefan du läste kanske?
Nej.
En sån.
Men jag tror någon aning om det. Jag har inte hunnit titta på det, men det är väl med de här routing-grejerna. Man ska sätta upp emellan de olika delarna.
Ja, sätta upp ett nätverk med 4.
Det ingår ju sedan i min nästa kurs, administration.
Ja, just det.
Så att jag har lite aning om det. Utan att egentligen
Ja.
så att den är ju faktiskt lite...
Så det är att de ska göra det lite.
Ja, den är jag nog lite mer intresserad av att göra faktiskt. Den kommer på nästa kurs. Då har man lite ben med där in i mest. Så att det är inte så dumt att göra det.
Bara mental krävs.
Det är några Och sen så lite till. Och lite till.
Ja, jag har testat en sån där på många år nu. När kom den som hype första gången? När var det?
Det var någon gång på 80-talet.
Var det 80-talet? Ja, kanske 80-talet. Ja.
Början av 80-talet.
Ja.
Det var ju någon...
Då satt alla på med dem.
Det var fan från Österrike.
Inte lika inne nu eller?
Jag tror det är Sheldon som har ställt till det.
Sheldon.
Big Bang Theory.
Ja.
Han gjorde ju en sån, någon av de sista avsnitten så gjorde han bytte lapparna på.
Jaha, ja.
Han löste det inte annars eller vadå?
Ja, så kom man ju på det. Ja, jag löste det, sa han. Jag har flyttat den lappen och den lappen.
Ja, det är väl bra att plocka isär någon och så bygga ihop igen.
Ja, jajamensan, det funkar.
Det är samma sluka såklart.
Olika lösningsmetoder.
Inte tidsmässigt.
Det är roligt att se de som gör det här på tid. De tar de här. Jag tror jag sitter någon som har gjort det med ögonbindel på. Han gjorde en världsrekord. Jag vet inte hur många sådana han gjorde på. Ja, det var bara några minuter.
Ja, något ska man bli duktig på.
Ja. Det gäller att hitta sitt i världen.
Ja, precis. Och ni satsar hårt på att vara rubrik 1000 är duktiga på det.
Ja, det här är min backup-plan.
De vill länsa på arbetsmässorna.
Skicka inte jag stabila strömmar i framtiden så blir det här mitt go-to.
Ja, då var det det.
På arbetsintervju bara du, har du läst vad jag kan?
Det här,
Ja, men det är problemlösning så det är ju inte helt värdelöst inom IT-industrin.
Det kommer ju jättemassa sådana. Det kommer någon sån här orm som man också kunde bygga ihop.
Just det, ja, precis. Stämmer det.
Kan man bygga ihop en kub och sånt här. Eller...
Skulle man få den rak eller skulle man få den med en
Ja,
färger på varje sida?
det var något sånt. Du kunde bygga ihop den som nästan en boll.
Ja.
Det kom ju en hel massa sådana.
men du har fått det innan?
Ja, men jag glömde bort det.
Det var nästan lika populärt som Donkey Kong.
Alltså jag tycker den är jättebra. Och det är bättre att börja med den direkt innan man gör arbetet.
Just det.
Jag ska kolla att det finns ju fler.
Ja, det är det.
Men lärare finns verkligen.
Så. Nej.
Har ni en sån? Ja. Fast jag har sett någon annan variant men också som där var lite mer trekantiga har för mig.
Ja, sen nästan ut som bågkäpp i Star Trek. De här runda.
Den kanske det är snarare.
Ja, det har de.
Ja, precis.
Jag tror jag ska kolla på 10.
Ja, det finns många påhittiga saker.
Hur kan den? Är det inte skönt? Ja, jag tänkte.
Jag måste rapportera.
Han sa ju i senaste videon jag kollade så här, av de 3 tjänsterna om vi vill göra det.
Okej. 5 sekunder, så drar strömmen igång igen. Okay, so back to the lecture. And now we move on to the next part, which is IP telephony, which of course is quite related because IP telephony is a streamed media then, an audio stream. But we'll look at our quite a lot of different protocols made especially for IP telephony. So IP telephony or voice over IP. We talked about before that network history have 2 different entry points. We have the telephone companies and their previous idea to build telephone networks. And then we have the network companies who want to build data networks. And so they come from different historical background. They have different ideas on what the network should be used for and how to implement it. And IP telephony is one of these areas where they really clash with each other, because voice over IP is of course something that can be seen as a network thing, but it can be seen as telephony, just that it's over the network then. So here we have competing standards from the telephone companies and from the internet side. So we have ITU, the Internet Telecom Union, which is a union of all the major telephone companies in the world who create standards for telephone. And we have IETF, which are the standardization organization for the RFC standards for internet. They have agreed on some things. They have agreed that the pulse code modulation for audio encoding is probably a good way, which means that we have this 64 kilobit stream for audio. That is something that we have agreed on. And they also actually agreed that we should use RTP for the transmission to mark up the sequence numbers and timestamps. But the rest they don't agree on. And mainly they don't agree on what is called signaling. And in signaling we have the entire part that talks about how do you set up a phone call? How do you find a subscriber to a certain phone call? How do you handle payment of phone calls? How do you handle the bridge between internet and ordinary telephone networks if you want to phone from internet to normal phone or vice versa? All of that needs signaling. It needs a way to agree and find each other and agree how to handle all of these things. And for those things they do not agree. The normal telephone system is called then the public switch telephone system, PSTN. So, as I said, there are things that we need to do if you want to set up a call. Map a phone number to a location. Before we had mobile phones, that was very easy in the telephone world because a location was the end of a physical wire. You couldn't move it around, it was always in the same place. On internet, that is not the case. I mean, what is the end place on internet? An end place is typically an IP address, right? And an IP address can be moved around. And to make it even more complicated, a client can move from one network to another and get a new IP address. But it should still be the end of a certain phone call that is going on. So mapping a phone number to a location is not so easy on the internet. And then you need to also to find the route to it, because you need to send the data stream to it. And as long as we just look at that as an IP number, we can of course use normal routing for IP. But if we don't look at it as a normal IP number, then we need to handle routing some other way. Accounting billing, as I said. Call forwarding could also be something, or different services like having a phone recording of incoming calls and notification that I'm on vacation, whatever. All of these different services can also be handled with signaling. In the telephone system, this is called SS7, Signaling System 7. So that is what we use in the normal telephone world. For IETF though, then, for internet purposes, we instead use something called SIP, Session Initialization Protocol. And the main idea here is that we should be able to find a subscriber or a phone, then a voice over IP phone with a domain name. And for a fixed phone, that is then easy, of course. I mean, you put a domain name, you combine that or link that to an IP address, and when you want to call someone, you just look up the domain name, you get the IP address, and then you can send it. But as I said, a phone can move around and get a new IP address. So that means that we need to be able to update the domain name system whenever a phone is moving, for instance. But things that can be done with SIP then is like phones, we call them a user agent, that is the client. So we can make or terminate calls. We can use a location service to find another phone. We have something called proxy service, and that is the main way to handle moving phones. We send to a fixed one, then that is proxy forwarded to different locations when we move around. We can handle certain types of numbers like these 800 numbers, toll-free numbers in United States, or such things that can also be handled by SIP. So the idea is that it should handle the same type of requirements that we need for normally phone on normal phone systems. The ITU approach then instead, because they have of course their own telephone systems, but they also want to be able to use the internet to forward phone calls. And their standard to handle the same thing as SIP here is called H323 instead. So roughly it tries to handle the same thing. We should be able to set up a call. We should be able to handle forward of calls. We should be able to handle the link between internet and the normal phone system and so on. So all of these services should be here. But they are done in a different way, and they are called other things. So here we have what we call a terminal. We have a gatekeeper between the internet and the normal phone system. And we have something called a multi-point control unit to handle different type of conference and other services around phone calls. If you now have an internet phone then, a voice over IP phone, these two standards are not compatible with each other. So you couldn't have a SIP phone and an H323 phone that can talk to each other directly. It can work if you go through a gateway somewhere, but they couldn't communicate directly with each other. So they are really separate standards. But to try to get something to be, at least so we know what we're talking about, there have been an agreement here. something called International Soft Switch Consortium. I don't think it exists anymore actually. It has been upgraded into new consortium, so I'm not sure exactly what it's called right now. But they have agreed, and the terminology is still working actually, that we agreed. So they agreed on that we should be able to do certain things on networks, so we know, and then different standards can be linked to this, so we know what we are talking about at least. So they are talking about 10 different functions that we should be able to implement regardless of what standard we are doing. And so they talk about these things like call progress, use of multimedia, use of data, support, routing, signal transport, and then continue with signaling, registration, audio, video, data security. So there are things that we need to be able to handle, and then we can implement in different ways. And here we see some of the possible protocols that we can actually use, some of the standards. We can see that we need to work on different layers. When we start at the bottom here with layer 3. Here, so this is the layer in terms of TCP/IP protocol stack then. So here we have, for instance, IP, we have resource reservation, we have the IGMP where we can connect to a multicast stream. So these are at the bottom for all the different protocols, which is not surprising since the idea is that we should be able to send phone calls over internet, which means that we need to use at the bottom what we have on internet, and for the network layer we have IP. We don't have an alternative really. On level 4 then, the transport, we again have what we normally have, TCP and UDP. But I think Morgan talked about that there are actually other transport protocols out there. It's not only UDP and TCP, there are alternatives. There are some more research network or protocols, and there are some that are actually used but not so much. So we have this one, for instance, SCTP, which is an alternative to TCP, which have some advantages over TCP. It's not used much, but it is an alternative. And when we set up a network connection, we of course can choose whatever transport protocol we want, as long as both sides are agreeing on what transport protocol to use. But the real mess starts at the application layer here, when we have lots of different protocols. So if you start with call progress here, for instance, you see that we have from the ITU world, we have this H323, and we have SIP from the IETF world. And then there are some other that we may also use. For use of multimedia, we have RTP, which is that both actually agree on, so everyone is using that. There's something called user data, that is some type of directory of users, how to find that. So here we have one protocol, as we call T120. We have some supporting protocols to manage streams, as we already talked about. Some of them are used for ITU, some are used for IETF. Routing, how to find the phone. We'll come back to those two. Signal transport, we have something called SIGTRAN. That's mainly used for ITU networks. And if we go into this H323 that we have in call progress, that is actually not only a protocol for call progress. It's actually quite a large set of protocols that is part of this H323. So if we go into the details here, we see that within that standard we have substandards for signaling, we have it for audio, video signals and so on. All of it are related to this H323. If you looked at different video conferencing applications or voice over IP applications, you've probably seen some of these protocols mentioned, because they often talk about, okay, we support these, and if you go into configuration, you can configure which you prefer and so on. So a lot of these are supported by different applications, but none support everything, which is a mess. So if you look a little bit on how they relate to each other here, we have for signaling here at the left, we have either this 3-to-3 or SIP, depending if we come from the ITU world or the IETF world. Both are using TCP, and SIP is also using UDP. At the bottom of that, of course, from IP and down, they are similar, because they will be carried over whatever physical network we're using. It doesn't matter what we have here, so anything can be supported here. As long as we get through the IP, it doesn't really matter what we're doing up here. For quality of service, we can use this RSVP or the RTCP to give feedback on the quality of service. And for media transport, there are different types of media encryption, media encoding, like MPEG and this H.261. There are lots of different standards, as I mentioned before, on how to actually encode and possibly encrypt and compress different type of media streams. And they are then using RTP, all of them, to actually transport them. Normally, they're using RTP at least. So even if they are from two different worlds and they are signaling different ways, otherwise things are quite similar, regardless of where you come from. But there are lots of different standards that you need to support in order to set up something that works in all aspects. The phone number, let's look lastly at that a little bit. So both these standards, the TRIP and ENUM, come from IETF. So the idea is that on the internet, how do you find a moving voice over IP phone? So TRIP relies on the location server to exchange information. So there is somewhere a location server we can contact and get the information about where is this phone, while ENUM instead uses the DNS system. And if we go a little bit more on details here, so TRIP, that is that we have a location server. Whenever we want to make a call, we contact that location service, and that should have then knowledge about where phones are, which means that they need to call back and tell the location service where they are. So it's always a communication between location service and all the different phones that are moving around. And as you see, it was built similar to BGP that we have on internet for routing of data, the Border Gateway Protocol, with autonomous systems, and that we need to just move around the autonomous system, and then the details of routing would be handled within each autonomous system. In reality, TRIP never really got used very much, and today it's obsolete. So instead, what is used mainly is this other one, the ENUM, or E164 number to URI mapping. So that translates a phone number into an internet address. So it is that if you have a phone number, that is a normal phone number that can be called on a normal phone. If you see that that phone is actually a voice over IP phone, you have to go to a gateway, and then that gateway will, as the example down here, map that phone number into a domain name address, and then make a reverse lookup of that to get the IP address of that phone, the current IP address. Which means that what the phone needs to do if it moves around is update a DNS server, the record in the DNS server to be found. So this is used, this is working. Since it's using the normal DNS system that we already have, it was quite easy to get to work. We don't have to really install any new type of service. The only thing we need to do is make sure that we actually update the DNS server correctly. Yes?
Question about, see if I can fix this together, but if you take, for example, you're out walking with your computer for some strange reason, and you switch networks, then you get a new IP number.
Then you get
with the call.
Yeah. Well, that is not handled by, of course, the enum. What if you move around and you say you get a new network and you get a new IP number, then you will have to update the DNS server. But that wouldn't help your ongoing call if you have an ongoing call, which means that to handle that situation, you would need to have in the streaming protocol, when you're talking here, you will need to have a control channel where you can send that I will now move from this IP to other IP. So to save an ongoing stream, you would have to do that. Or as an alternative, you can use a proxy server. So the phone on the other end actually talks to a proxy server that is fixed. And then it's just between you and a proxy server that need to be changed. The other side doesn't need to know. It's only you and your proxy server who need to handle the change of IP address. So that is how it can be handled. But if you look at reality, it's sometimes these ongoing streams break down when you move, and sometimes they don't. So it depends on how they implemented it, if it works or not. Have you used voice over IP much? Do you use it at home instead of normal phones, or no? I mean, people today normally use wireless phones instead. But you probably, well, I think it's implemented here in Kalmar actually, that if you have Telia as your mobile phone operator, and you're inside here and you lose the 3G connection, your telephone call can be routed over internet instead. And it works automatically actually. So that is something that we do today, and that works seamlessly actually. Right. I think that was the last slide, yeah, and then there was summaries that we already talked about. So any questions about multimedia streaming, or can we stop for today? Okay. So next lecture will be from Växjö, so I see you on the stream. Bye.